thank you for your time. And I will try to, we have a presentation and these are the topics. I will try to use the presentation as the least as possible. And if you are not in a noisy environment, you can keep your microphone open and you can interrupt me and ask questions.
I mean, I'm probably going to have to do some ASHRAE stuff.
I hear some feedback, but maybe it's only me. And so let's start. Again, if you have questions, you can either type them in the chat box and we will answer them, or you can just interrupt me anytime and we will talk about that. So these are the arguments. These are the topics that we will try to go through today. Introduction to gasketed plate and frame heat exchangers, the log mean temperature difference, which is the temperature approach, essentially, the importance of pressure drop, shear stress, what it is and why it's so important. It's one of the most important things that we will go through today. And then we will talk about the Hri certification, what it is, and again, why it's important and how actually we introduce that. We're talking about gasketed plate and frame heat exchangers. I assume that most of all are somehow familiar with them, but I will have a very brief introduction of very basic information, and maybe for some of you it will be kind of redundant, but I think it's important that we cover all the basics. So a plate and frame heat exchanger is what essentially you see here. It's made of, as by the name suggests, two main components, the frame and the plates. The way that is designed, normally the price of the cost of the heat exchanger is more or less split 50-50 between the cost of the frame and the cost of the plates. If you have a fairly large heat exchanger with fewer plates, of course, the relative cost of the frame goes up compared to the cost of the plates. We will see a little later why this is important. But these are the main components that you can see here. And I assume that you can see my cursor. This is the front plate. This is the back plate, the carrying bar, the feet, the bolts and nuts. The only reason why I mentioned the feet is because they are a key component if you have seismic requirements. For the 99%, all that you need to do if you have seismic requirements is to use reinforced feet. In some extremely rare case, you need actually to use either reinforced frames or reinforced flanges. But I live and work in California, which is pretty seismic, and I've never seen them. But in theory, it is possible. And the way that a heat exchanger works, as you can see here, of course, you have two sides. You have four connections, two for the hot side and two for the cold side. Of course, the inlet and outlet of the hot side and the inlet and the outlet of the cold side. And if you notice here, this gasket seals this plate and it doesn't seal this plate, and then seals this plate, doesn't seal this plate. So you pump the hot fluid through this channel, and then it trickles down depending on whether the gasket is on or not. And here I have a plate, you can see here. So this is how it works. You have, as that picture shows, you have all these plates one after another, and you pump the fluid through this hole here, so like this. And of course, this is the gap. It's very, very tiny, as you can see here, but this is the gap where the fluid goes up and down. One face of the plate is hot, and the other face of the plate is cold, and they are countercurrent. You can design a heat exchanger to be co-current, but again, 99% of the cases you go actually countercurrent. So the hot fluid goes down and the cold fluid goes up. Go back to there are a few considerations when we talk about that, and it's pretty intuitive. Now let me go back here. Pretty intuitive, as you can imagine. as you can see here, the inlet. So in this case, the inlet is here, and so it's offset, and you have to distribute the fluid through the whole plate, and then it gets out from the bottom. And because it's offset, the distribution of the fluid equally across the plate is actually pretty challenging, and that's the reason why you have this area, which, as you can see, has a completely different design to this area. This is the distribution area, and this is what it's called the heat transfer area. Of course, you have the heat transfer across the whole plate, but this is the main heat transfer area, and it's called the distribution area. And the distribution area is a key component of the efficiency of a heat exchanger. The other critical part that you have, and this is where I use my drawing skills, is that so we said that you have the front plate where you have the connection here, connections, and then you have the pressure plate in the back. And then you have the hot going in, and every other plate goes down. And then you have the cold going in, and every other plate, it goes up. You can see my whiteboard, right?
Yes.
Okay. So, as you can see in the picture, as you can see in this picture, you have very different sizes of heat exchanger. These are very large heat exchangers. The one on your right, this is a 32 megawatt heat exchanger, one single heat exchanger, and it has 800 plates. The other one on your left, it's about a 10 megawatt heat exchanger, or both of them are in data centers in the US. And but the point that I'm trying to make here is that if you look at this, so this here is the connection, and here is the distribution channel. This is the distribution inside of the heat exchanger. So if you have 800 plates, like in that case, as you can imagine, this distribution is pretty long. So you have to design the plate pack in a way that you facilitate an equal distribution throughout the plate pack. It's very fundamental that you have an equal distribution through the plate, but it's equally important that you have an even distribution throughout the length of the plate pack. Now, how do you do that? There are many different tricks, but the most common is that if you see these two plates, you might notice that the angle of this chevron path is different. This is, let's say, more, so this is more open and this is more closed. Now, if you remember, the fluid goes this direction. So if you imagine this chevron path as speed bumps, you can easily understand that the ones that it's more horizontal, it's more effective as a speed bump, and the one that is more vertical is less effective as a speed bump. These are called high theta and low theta plates, and they influence the pressure drop of the plate pack and the shear stress. We will talk about all these concepts in the future, but let's say for the moment, keep in mind that they influence the pressure drop. So because they influence the pressure drop and they influence the efficiency of the plate pack, the higher the pressure drop it is, the higher efficiency is the plate pack, but normally you don't have, unfortunately, all the pressure drop that you want. So you have to play with both of them, and you can mix them. You can have a plate pack that is mixed of a high theta and low theta plates, or you have a plate pack that is all made of one kind of plates, which normally means that you need more plates. If you mix them, so you have a higher efficiency plate pack, and you want to distribute the fluid effectively and efficiently throughout the length of the plate pack, obviously you want to put the higher pressure drop plates in front of the plate pack so that you don't have, let's say, a path of less resistance here, and you have the vast majority of the fluid going here, and then you have very trickle fluid left for the bottom. So you want the higher pressure drop plates in the front of the pack, and then you want the lower pressure drop plates at the bottom of the pack, so you facilitate an equal distribution of the fluid throughout the plate pack. Does that make sense? Any question?
Sounds good.
Okay. Now, the other important concept here with this drawing is that you see that you have an equal number of channels. We call them these gaps between the plates. For us are channels. So you have the equal number of channels for the hot side and the cold side. That means that kind of by default, a plate and frame heat exchanger works best when the flow rate between the two sides are comparable. Meaning that if you have, use different colors so it's clear. If you have 1000 GPM on the cold side, and you have 100 GPM on the cold side, one of these two sides is not efficient. And normally what happens is that, of course, the low number one is the least efficiency, because you have to design the heat exchanger to accommodate the larger flow rate, and therefore you have a way oversized heat exchanger for the lower flow rate. Now, in this case, it is particularly bad because the cold side, in most cases, particularly when we talk about cooling, but generally the cold side is the most challenging because it comes from a cooling tower. And particularly if it comes from an open evaporative cooling tower, we all know that that water is kind of a receptacle for dust, sand, seeds, any kind of contaminants that you have in the air, they end up in that water. And so that water progressively gets dirtier and dirtier, and you have those very tiny gaps here between the plates that you can imagine the heat exchanger. Unfortunately, it's a very effective filter. So if you have a lower flow rate in the cold side, and you have the heat exchanger designed for 1000 GPM, and the cold side is 100 GPM, and you have an oversized heat exchanger, it's like that you have a way larger pipe for your fluid that you wouldn't actually need. That means that you have essentially laminar flow through the whole heat exchanger, or you have a very, very low turbulence. And we will see later that turbulence is a key aspect of keeping the heat exchanger clean. So let's say, in any case, the takeaway of this section, the first section, is that I'm going to skip a lot of slides here, but the takeaway of this section is that plate heat exchangers work best when you have similar flow. You can say here, the red part, sorry. You have similar flow on both sides. I expect a question here. No questions? All right. The question that I'm asked normally in this part of the presentation is that, well, what happens when I do have different flow rates in heat exchangers? Because it happens, it's possible. So there are a few tricks that we can employ. If you have this kind of unbalanced 1000 and 100, there's very little that that we can do. But if you have, let's say, 40, 30, 40, 50% unbalance, if you have 1,000 GPM one side and 600 GPM the other side or something like that, we can play with the configuration of the plates and the low theta and high theta, and mix them in a way that actually it makes a little more sense. Or even more effectively, for many sizes, Alfa Laval has what's there called asymmetrical plates, meaning that one of these channels is actually much bigger than the other one. And that is, of course, has been specifically designed if you have an unbalanced flow rate. So, of course, you put the higher flow rate in the wider channel, then you put the lower flow rate in the lower channel, and that you minimize the effect of an unbalanced flow rate through the heat exchanger. No questions?
We got one question, Cosimo.
Yes.
The question is that Mick says, was curious about limitation on pressure differentials between the two systems. Can we have one side at 100 PSI and the other at 20 PSI, given the flow rates are similar?
That is not a problem. Plate and frame heat exchangers are tested with 100% pressure rated one side and 0 the other one. So pressure differential is not a problem. Mechanically speaking, for the heat exchanger, is not a problem. Process-wise, it's an excellent question. Process-wise, you want, of course, to have the highest possible pressure drop in the most fouling-prone side of the heat exchanger. And this is, it sounds like a detail, but it's very important because, as I said, the biggest problem, and we will talk about that ad nauseum, we will talk about that a lot during the presentation, but the biggest problem that you have in plate and frame heat exchanger is fouling, is that they act like a filter. And you can absolutely prevent that. Plate and frame heat exchangers are used in applications that you wouldn't believe. They are used in sugar plants where they run molasses through the plate and frame heat exchanger, and they don't foul. And they are using in oil and gas, and using with petroleum that is very thick, full of particles material, and they don't foul. The reason is that they are designed, the heat exchanger, the two sides are designed for 1,000 GPM, and they run them at 1,000 GPM all the time. They do not do partial loads. If it's designed for 5,000 GPM, it runs at 5,000 GPM. That is really important because, as you can imagine, you keep the heat exchanger, the velocity through the channels, it's so high that you have that turbulence. And again, we will talk about that ad nauseum, but they have the turbulence and keeps the heat exchanger very clean all the time. So if you have an unbalanced pressure drop between the two sides, mechanically is not a problem. Process-wise, it could be a problem if the lowest one is the side that is more fouling prone. If you do not have fouling concerns, for instance, if you have ammonia on one side and you have a closed loop water at the other side, it's not a problem because they're going to stay clean all the time. You don't have fouling issues, and you can live with an extremely low pressure drop and you're okay. But unfortunately, experience tells us that these are very rare occurrences, and fouling happens, and so you have to take in consideration that eventuality. I don't know if I answered the question.
I think so. If there's follow-up. There's a follow-up question from Mick. He asks, does Alfa Laval have a steam to water flat plate system? Can you do steam on one side and water on the other?
Sure. Yeah, absolutely. We have steam. We have heat exchangers that are designed specifically for steam. It is very hard to find an application where you cannot use a plate and frame heat exchanger. Temperature-wise, the gaskets are the limitation, of course, as you can imagine, being not metal. But you can go up, like, I think 400 Fahrenheit or even higher with some very special gaskets. Pressure-wise, we go up to 900 psi. They can be rated to up to 900 psi. We have a vast range of materials, and I'm talking about Alfa Laval, but to be honest with you, every vendor has, of course, 314, 304, 316. You have SMO, you have titanium, you have nickel, you have carbide. You can, I mean, literally, you can have. We have from sulfuric acid, 40% sulfuric acid at 190 degrees going through a heat exchanger, to HVAC, which is water to water, very mild application. And so you have from the most corrosive, you have, of course, seawater. So steam is absolutely normal, yes.
Okay, great. I know this is my question, just follow up on that. And I know your experience is on the cooling side mostly, but a lot of specifications we see for steam to water heat exchangers are shell and tube and not frame. Do you have anything to say about where you would want to choose a plate and frame instead of a shell and tube?
I would say that you want to use a plate and frame almost everywhere. Shell and tubes are commonly specified for steam because they are kind of legacy heat exchangers, and people feel more comfortable using shell and tubes. But there's no technical reason not to use. I literally cannot imagine a situation where a plate and frame doesn't make more sense. There's only one application where actually shell and tube is still the winning choice, and it's in oil and gas. If you have an extremely large carbon steel or carbon steel heat exchanger, it is 4 times bigger in terms of footprint, but it's still cheaper. Other than that, but I'm talking about heat exchanger that are the size of a 18-wheeler. For a small shell and tube or this size shell and tube for a steam application that you can find in the application, kind of application that you see, it doesn't make any sense not to use a very small, this size, brazed for the most part, heat exchanger. And if it's larger, and if you want to have the extra capacity of the extra feature that you want to open and clean it, you can use gaskets. That's not a problem. But it's very common to use plate and frame, either brazed or gasketed in steam applications.
Great.
There's no technical reason to keep using shell and tubes.
Okay. We probably got about 20 minutes before we want to do Q&A at the end.
Yes. Unfortunately, yes, we lost a few minutes. So let's talk about LMTD and temperature approach. So these are the formulas. I will send the presentation. You can look at the formulas as much as you want. Let me skip this part, particularly because we are in a rush. So the formula, the name is LMTD, which stands for, as I said, logarithmic log mean temperature difference. It's a logarithmic curve, as you can see here in this picture. And and as such, in an area of the curve, a small variation implies a huge effect. And that is, unfortunately, of course, the area where we have the most common opportunities. So let me start with the very basic. You understand the concept. I mean, you understand why you want to use a close as possible temperature approach, I assume. But let me spell it out for you. Assuming that this is your building, could be a building, could be a data center, doesn't matter. It's a box that you want to keep at 72 degrees. And normally what you have a chiller that generates cold water. That generates cold water, and then the cold water is pumped into the building, and it's used to cool down the building. Of course, what happens is that at times the temperature of the air outside is lower than 72 degrees. So you say, why do I have to run the chiller all the time when the temperature outside is 40 degrees? So why I cannot use the temperature outside? So what it's commonly done is that you have a cooling tower, and for the most part they are evaporative, but they can be air cooled, so closed loop. It doesn't matter. You have a cooling tower. You break this loop here. You decouple, and here you have a heat exchanger, and then you have here another loop that goes to the cooling tower. And when the temperature of the air is favorable, you don't run the chiller, which is a compressor, of course, so it uses a lot of energy, and you run the cooling tower. It's called free cooling. Of course, it's not free because you have to run some pumps, but compared to the cost of running the chill, it's called free cooling. So the problem, so you can use this when the temperature is 40 degrees, 50 degrees. So you have 40, then it goes up to 50, then 60, then it starts to get closer and closer. Of course, the temperature approach that we were talking before starts to get closer and closer. But if you have a 1 degree temperature approach, and give me some rope here, it's not this perfect, but let's say if you have a 1 degree temperature approach, you can use the outside air instead of the chiller up until the outside area, of course, it's 71. If you have a 2 degrees, you can use the outside air up until it actually gets to 70 degrees. So you use less for a shorter period of time, the advantages of the outside air. That's the reason why they always try to have the closest possible temperature approach that is technically doable. But, and here it's where the rubber hits the road. So, but because this is a logarithmic curve, what happens is that if you are in this area of the curve, a small variation of the temperature approach, it means that you have a huge increase of the size of the heat exchanger. So at 0 temperature difference, the heat exchanger is infinite in size, of course. At 0.5 temperature difference, the heat exchanger is extremely large. Then if you go between 5 and 6, it doesn't make that much of a difference. But for the most part in HVAC, we play between 2 and 3. And I would say even between 1.5 and 2.5. And as you can see here, in this range, even a very small variation implies a significant difference in the size of the heat exchanger. And this is a real example. You have here on the left an example. This is just a size. So you go from 56 to 42, the hot side, from 40 to 54, the cold side, and you have a certain heat transfer area, and price is 100%. If I open up these two curves, and instead of having a 2 degrees temperature approach, I have a 2.5, a 0.5 difference. Now, I challenge you in real life even to measure 0.5 difference. But a 0.5 temperature difference implies that the heat exchanger is almost 30% smaller and almost 30% less expensive. If you go farther, and if you actually turn into a 3 degrees. So if you open up even a little more, and now it's 3 degrees, it's about 40% smaller and less expensive. Now, as we said before, the HVAC, it's a very kind of mild application for a heat exchanger. So what vendors noticed, and not much of Laval, I have to say, but let's say what vendors noticed is that you ask me for a duty and I design a heat exchanger for you that actually it's 0.5 difference off of what you ask me. I don't tell you. I tell you that the heat exchanger is designed exactly for your duty, but I'm providing you a heat exchanger that actually is designed for a duty that is 0.5 degrees higher, and all of a sudden, I'm 30% more competitive than all the other vendors. And people notice that. So they started playing with that. So 0.5 then became 0.6, then the 0.6 became 0.7. And that became almost impossible to compare apple to apple. And that is where the Hri certification stepped in. So the Hri certification is a consortium of vendors. So it's a private consortium that we decided to say, okay, we need to level the field here because it's became impossible to actually do a serious job. And so the Hri has it guarantees you that if you give me a duty, the heat exchanger, if it's Hri certified, is actually designed exactly for that duty. And if you want a proof of that, is that if you ask for the same duty, a heat exchanger that is Hri certified and a heat exchanger that is not Hri certified, the Hri certified heat exchanger is 20, 30, 40% more expensive, not because it's made of different materials or not because it's painted in gold. There's no other reason. The only reason is that normally it's much bigger because it's designed exactly for what it's supposed to do instead of what we think we can get we can leave without you noticing. So that is actually the real catch of the Hri certification. And that is the reason why there's an application where it's mandatory. If it's HVAC up to 20,000 GPM, and if it's and now includes glycol. So if it's glycol, seawater, and water, and HVAC, it's mandatory. But even in my business, which is data centers, which of course would not be mandatory to use Hri, everybody, it's not even a question anymore. They all want Hri certified heat exchangers because it's a guarantee for them that the heat exchangers will actually perform as expected. Questions?
No other questions yet, but everybody feel free to put them in the chat window or speak up if you have them.
Okay. The other important aspect of all this concept is that, and it goes kind of back to this thing. If you have a high season and a low season, you end up using the heat exchanger for the most part at partial load, because of course you design the whole cooling system for those 2, 3, 4, 6 weeks in summertime if it's cooling, or if it's heating for those very cold weeks during the winter. But that inevitably, of course, you use the cooling or the heating system at partial load for the rest of the year. Partial load is particularly tricky if you have fouling issues, because as we said, you have the velocity through the channels as it's lower. So ideally, what you want to do if you have really 2 different seasons is to split the load into 2 smaller heat exchangers, 50% of the capacity, twice, because at that point you can run one heat exchanger when it's at partial load, and you can run both of them when it is at full load. This is ideally the best design that you can achieve, each heat exchanger with their own pump, so you can control the flow. I have to tell you that in reality, it doesn't happen very often for a number of reasons, obvious reasons. It's significantly more expensive. the heat exchangers by themselves, maybe they're not even much more than one big heat exchanger compared to two smaller. Yeah, the two smallers are more expensive, but not even that much. But of course, you have more pumps, you have more piping, the footprint is larger. There are a lot of other advantages if you have the two 50-50 design. Of course, the heat exchangers are smaller, so maintenance it's easier. You have redundancy. You have more flexibility on where to put smaller heat exchangers, but you need more space and you need more money. So I have to tell you that is the ideal design, and if you can do that, definitely go for that. But in reality, it's not very common. No, I want to skip this because we don't have a lot of time. Pressure drop. These two concepts, the pressure drop and the shear stress, they go hand in hand. And there's a few things that I want to talk about when we talk about pressure drop. So the first one is that the first concept, very important about pressure drop, is that this is the formula, etc., etc. We can go through the formula. You can go through the formula when I send you the presentation. But pressure drop, you design the heat exchanger for 1,000 GPM, and then you run it at 500 GPM. You design it for 1,000 GPM. With 10 psi pressure drop, but then you run it most of the time at 500 GPM. So at 1/2 of the throughput, the pressure drop decreases with the square of the difference of the flow rate. So if you have 10 psi at 1,000 GPM, at 500 GPM, you have 2.5, because it's 1/4, because it's the square of the difference. This is really important because that should tell you that 5 psi pressure drop to begin with is really not enough, because that means that 5 psi, you end up with 1.25 or less psi real pressure drop in most cases, and that is not good. Again, assuming that you have fouling issues. If you do not have fouling issues, you can live with whatever pressure drop you have. I have seen 0.9 psi pressure drop to begin with, but that's because that was ultra pure water in a cheap factory where they do microprocessors, and that water, it stays clean all their life. It's the cleanest water you can even imagine. So fouling is not an issue. But if you have an open cooling tower and you start with 5 psi, that heat exchanger will need to be cleaned every 2 years at best. And that is a financial and an economical consideration. I'm not saying that it's wrong, but it needs to be factored in. You save pumping costs, and so you save power if you have a lower pressure drop, but you need much more maintenance. So you have longer downtime, and then you have to call in technicians to open and clean the heat exchangers. And on top of that, it could be unpredictable how often you have to open and clean the heat exchanger. So it is a little more challenging. So we see time and time again HVAC applications where they ask for 5 psi pressure drop to begin with. We strongly discourage that, but eventually it's the decision. As long as the end user has all the information, then it's their decision which way they want to go. That being said, there's another important aspect here. So you have kind of the pressure drop can happen in two different parts of the heat exchanger. One is good and one is bad. Remember when I told you that about 50% of the cost is in the frame And if you don't have a large number of plates, actually that relevant cost actually goes higher. It could be even 75% of the total cost is in the frame. And the size of the frame is mainly driven, of course, by the size of the ports. So a heat exchanger with smaller ports will always be less expensive than a heat exchanger with larger ports. This is important because if you give me a duty, particularly HVAC, which is really price sensitive, I always will try to squeeze that duty in the smallest possible heat exchanger. With a higher number of plates, but the frame is going to be the smallest possible that I can. Which means that it might happen that sometimes I have maybe a 10-inch pipe that I have to squeeze down into a, well, no, this is an extreme, but of course, if I can pick these two heat exchangers, and I can either use this size with 20 plates or this size with 150 plates, this solution is always going to be significantly cheaper than this solution. So it is possible that I have to squeeze a 10-inch pipe down to a 6-inch port. But at the point, as you can imagine, if I have a flange here and I squeeze it down to this port, you have a lot of pressure drop at the port. And that doesn't help anybody. It's just waste energy. Because the pressure drop that you want is actually, it's here. You want the pressure drop of the fluid that goes to this plate. And that point is where you want the pressure drop. So be mindful, if you happen to receive two quotes from two different vendors, and one has a higher size port and one has a smaller size port, even if the higher size port is a little more expensive, that it's always going to be the best design. Of course, if you have a 10-inch pipe and the port is 14 inches, it doesn't help anybody. I mean, that's but it will never happen. You will always have it. If you have these, if you see this, it's always going to be, you have to squeeze down the pipe into a smaller port. And if it's too small, that will cause problems. I'm going very fast here, but because I have a few minutes and I want to make at least the next point. So here, the takeaway of all this pressure drop presentation, as part of the presentation, is give us the highest pressure drop that you can. That is always preferable. And just as a reference, unless you really know that it's going to be clean, that it's clean to begin with, it's going to stay clean for years, 5 psi is not recommended. Then it's your decision. Let's say it's the end user decision. And this is the last very important concept that we have to talk about today. And two things. Fouling factors. Fouling factors, they have been designed years ago. They have been thought years ago and then applied specifically for shelling tubes. Fouling factors do not work. I mean, you can apply them, but they have not really been designed, and they essentially do not work for plate and frame heat exchangers. But because of the different geometry of the plate and frame, you do not use fouling factors, because what they do is that they increase. If you apply for fouling factors, so the concept of the fouling factors is that you have some extra capacity. So in case that you foul part of the heat exchanger, you can always have extra capacity in the other part of the heat exchanger. Now, let's see why this is not a good idea. Here you have the front plate, as we have seen before, the back plate. Here you have your plates, and then you have your channels, inlet, hot inlet, and of course here you have the hot outlet, but because it's two-dimensional, I cannot draw that. And then here you have the cold side. So we said, let's assume that this is, as we said before, 1000 GPM heat exchanger. At 1000 GPM heat exchanger, you have a velocity to the channel that is X, doesn't really matter. But more importantly, you have, because of all these speed bumps in the plate, so the fluid goes this way, and it is forced to, by design, of course, to be turbulent. And so you have this, you have this fluid here that it's all turbulent like this against the wall of the plate. And remember that we are talking about a gap that is 2 millimeters. It's a very, very small gap. So this turbulence, it is what keeps the heat exchanger clean. And this is called shear stress. And it's measured in Pascal because it's literally, which is a pressure, it's literally the pressure of the fluid, of the sweeping effect of the fluid against the plate. Imagine that you design the heat exchanger for 1000 GPM, so you have a certain number of channels. And so you distribute 1000 GPM through 1000 channels, and you have 1 GPM per channel, let's say. If you apply fouling factors, what they do is that even a pretty regular fouling factor, which would be 0.005, you see this fouling factor pretty often. 0.005 in a plate and frame heat exchanger, depending on the size, but on average, increases the size of the heat exchanger 40%. So you have 40% more channels than you would have otherwise. Now, if everything that you want to do to prevent fouling is to keep this fluid to go fast enough to the channels, so you have this whipping effect, if you distribute the same flow rate through a higher number of channels, to a 40% higher number of channels, you actually slow down the velocity through the channels. So you're applying fouling factors in plate and frame heat exchangers to prevent fouling or to help with fouling. And actually what you do, you favor fouling. So I don't want to sound too blunt, but from our standpoint, when we see fouling factors applied, we know that the person who designed the heat exchanger and made that specification doesn't know anything about plate and frame heat exchangers. So if you don't remember anything from this presentation, please remember that you don't want to see or apply fouling factors in plate and frame heat exchangers. And when you want to facilitate and use as much as possible is this whipping effect called shear stress. So it is always a good idea to ask a vendor what is the shear stress of a heat exchanger. And every vendor, every software tells, our internal software, it tells us what is the shear stress of a heat exchanger. And it's always even a better idea to ask what is the shear stress at a couple of different capacities. Because if you have a shear stress at full capacity, 1000 GPM, which is pretty good, but then the shear stress drops significantly when it's at 500 GPM, that's good. It's a sign of trouble. And I will say that I don't want to sound like a broken record, but I'm talking about if you have fouling issues. If you don't have fouling issues, all this presentation is kind of a waste of time. But if you have fouling issues, and again, we see them as by far the most common problem.
Osimo, we have one question regarding
Yes.
channel flow velocity. Limits in shell and tubes are typically around 8 to 9 feet per second. Is that similar for plate and frame or something different?
So what we measure for the most part is the velocity at the ports, because that is a kind of an indication of the pressure drop at the ports. So where is the red one? So what we measure for the most part is the velocity here. And we say that to be safe, we don't want to go over about 16, 17 feet per second. You can go a little higher. Of course, the lower you put the threshold, the bigger ports you're going to have for the same duty. Of
Right.
course, yeah. So this is what we have seen.
But you said 16 to 17 feet per second?
Yeah, yeah.
Okay, so higher.
That is by default our software setup. We can actually push it over 20 and it's still pretty good. But this is something that we can do internally. We can do. I would not advise if you play with the software. I would not advise to change actually the setup
Okay.
on a regular basis, unless you are a very advanced user. At that point, you probably know more than we do.
Okay, great.
So one question that we are asked quite regularly when you talk about shear stress is that what is a good shear stress? And as you can imagine, no, let me use this. It's not a very easy question to answer because again, it depends on your application and how fouling your application is. Generally speaking, we say that 50 Pascal is a good number. If you are above 50 Pascal, you are pretty certain that the heat exchanger is not going to foul. And so if you are at 50 Pascal at full capacity, you can ask, okay, what is the shear stress at 800 and 600? And then you can see. For my application in data centers with open cooling towers, for instance, we have seen that 20 Pascal, it's bad news. You have fouling and you need to open the heat exchangers every couple of years. If you are between high 30 and 50, it could be acceptable. The problem is it really depends on the quality of your water, and that it's so dependent on project to project that it's very hard to give a number that it's applied everywhere. But let's say 50 could be a good starting point, but it's not set in stone. But ask this question when you spec a heat exchanger, regardless of the vendor, ask what is the shear stress of the heat exchangers at that capacity. We are at the top of the hour, and
yeah, I got one more question for you kind of on this topic. Is the turbulence of the fluid related to shear stress in the heat exchanger? I think the answer is yes.
Sorry, say that again.
Is the turbulence of the fluid related to the shear stress in the heat exchanger?
Yeah, the shear stress is an effect of the turbulence. So the higher is the turbulence, the higher the shear stress is going to be, and which has all advantages because you have it's more fouling resistant, and you have a higher heat transfer efficiency. Now, don't focus on the heat transfer efficiency because actually it's pretty good no matter what. Even if the shear stress is low, you're always going to have a very good heat transfer, because if it's a shear stress is low, it means that the velocity through the channels is low. It means that the residence time inside of the heat exchanger is high, it's longer, and so you have more time to exchange heat. So the heat transfer part is going to be good no matter what. It's the fouling resistance part that is really dependent on the shear stress.
Okay, great. Yeah, if anybody has any more questions, feel free to unmute yourself and ask those now. I'll give a couple minutes for that.
I can stay here as long as you want, but
okay, yeah. And hello? Yeah, while we're waiting for anybody to jump in or type a question in, I just wanted to let you all know we are trying to do some more trainings like this. So if you have topics that come to mind, projects that you're working on, things you'd like to learn more about, shoot us an email. You can email me, dan@norbrand.com, and let me know what you'd like to learn about. And we can try and put something together. We're also planning to start rolling out some shorter 15-minute technology spotlights, some new products, new features, things like that. And so hopefully we're planning to start those next Wednesday. We're going to call it our water cooler Wednesdays. So you can be watching for that. And again, anything that you have on your mind that you want us to focus on one of those, we'd be happy to do that.
I did have a question on the best practices for a good spec regarding like the heat exchanger wall thickness. And then do you have a chart on what gasket material to use for what fluid, like oil, water, steam?
Yes, we do. Yes. The thickness, both of them really good questions. So of course the thinness the plate is, the higher the efficiency of the heat transfer is, but it is so the difference is so minimal that it doesn't really apply. The other effect is that if you have a heat exchanger, so these are, let me see, this is a 0.4 millimeter, which is the most common thickness plate. So a 0.4 millimeter of this size makes perfect sense. If you have a heat exchanger that is, this size, that is what, 14 feet tall, a 0.4 millimeter plate, which is so wobbly that working with them, it's really, really hard. So it's a matter of what kind of fluid you have, what kind of corrosion and or erosion you might have in your fluid. It's the first thing that you want to consider when you talk about the thickness of the plates. But the other aspect is the ease of maintenance if you have to open and close the heat exchangers regularly. Now, in HVAC, it's such a mild application that we see heat exchangers going for like 10, 15 years with no maintenance whatsoever. So at that point, I mean, the maintenance considerations, of course, are kind of not relevant. But in other applications, they have to open them every 6 months. And at that point, you want to make the life of the people opening and closing the heat exchangers a little easier. And for the charts about the temperatures and the material for the gaskets, yes, we have those charts, those tables.
Thank you.
Let's see, Cosmo, one more question that we've had recently. What's the difference, or can you explain the difference between lined ports and unlined ports?
Yes. Let me see. Well, no, I don't have a picture, but so let me go back. Okay, so you see these holes here, and here. These, of course, are the ports. The frame is made of carbon steel, painted carbon steel, and the plates are made of stainless steel, all of them. So you can actually, here, you can have like a ring of the same material of the plates or higher. So if you have, for instance, we do not have 3 or 4 liners because we only use 316 liners. But if you have titanium plates, we're gonna use titanium liners because you want, of course, you try to prevent corrosion and you want to use the same material. But liners are only their job is to prevent that the liquid touches anything but stainless steel. So they touch, here you have a gasket and the pipe connects to the liner, and then here on the back, here you have another gasket and then gets into the plate pack, which is all stainless steel. It's a fairly inexpensive add. It's probably it depending on the size, of course, of the heat exchanger, but it could add from a few $100s to maybe $1,000 or $1,500 for very large heat exchangers. It's a kind of an extra protection for the corrosion of the frame of the heat exchanger. One question that I've asked all the time is that the pipe is carbon steel. So why should I line that little part of the heat exchanger to prevent the liquid from touching carbon steel while the pipe is carbon steel? It's a good point, but because if you, particularly if it doesn't run all the time, you can have water staying into crevices, and you can facilitate particularly aggressive corrosion or rusting, of course, on the frame of the heat exchanger, that in some cases are expensive. You're talking about $50, $60, $100, $250,000 heat exchanger. So, I mean, you save $1,500 not to line the ports, and then you might put at risk the whole heat exchanger. So, again, it's your decision. If you're really tight for money, you can avoid them. I would say 95% of the heat exchangers that we sell are with line ports.
Great, thank you. Okay, well, with that, we're gonna wrap it up. If you have any other questions, feel free to send those in via email, and we'll be happy to follow up with you. And appreciate you all taking time. Thank you, Cosimo, for joining us today.
Thank you, guys.
Yep, and wish you all a good rest of the afternoon and a good week. So again, hit us up if you need anything. Thank you.
Thank you. Take care.